Good day. My name is Elena. I'm more than 15 years, I believe, already in ML, working for blood research, blood enterprise, etc. And the 3 last years I devoted to the AI safety. And today I want to talk with you about the most, I believe, beautiful concept in AI safety, and at the same time the most scariest from my point of view. Concept in AI safety called Mesa Optimisation that occurs in some large models. The most beautiful part of it that with this concept we could explain and prove the possibility of all the scariest scenarios about, I don't know, AI doomers in our future. But from the other hand, this concept is technically proven, and we can technically search it, we can technically try it and try to find it in LMS models, etc. So in our agenda today is to look on this concept from the 2 points of view, from the thinkers or philosophers who proposed this concept, and from the point of view of engineers who try to implement ideas of those thinkers into some code, into some experiments, show us some numbers, etc. So, the Mesa optimization, what it is? This is some kind of internal optimization process that could occur in the LM models itself. In the same way as we use, for example, as we postpone some optimization problem and choose the base optimizer, like, I don't know, HDD, for example, or other kind of optimization algorithm to solve this optimization problem. The neural network, mighty neural network, could postpone its own optimization problem for itself and choose some kind of optimization to solve this problem. In the same way as we choose base objective to optimize, to find some extremums on it, the Mesa optimizer should postpone its own Mesa objective, but the problem occurs here when this Mesa objective isn't aligned with our base objective that we postpone when we train the model. To demonstrate what does it mean, there is example, I really like it, lazy not lazy robot. For example, we train some robot system that should clean our rooms, and we set up as base objective something function that feed the robot to maximize the removing dirt from the house. We expect that with this objective, robot should, I don't know, try to reach hardly reachable areas inside the room and find all kinds of dirty spots in the room. But that could really appears that instead of searching these hardly to reach areas in the room, robots start to bring some dirts from, I don't know, outside, for example, and only after that clear these dirts from the room, and that's how it got its base objective reward about maximizing removing dirt. The classical example here is all kind of gaming cheater that we already saw in the internet. Those AI cheaters exploits the bug, some glitch, I don't know, going through the walls, etc. I don't know, for example, if we train the robot on some base objective and reward it about the height of the bottom face of the block, we expect that the robot should put the red block up on the blue one, but instead robot just find this hack system and just flipped out the red block. The same situation here, if we use some shaping rewards and show, for example, the robot who plays this bot game, we can put some green blocks on the preferable trajectory that this bot should follow, and we want this bot to follow by these green blocks and learn the trajectory. Instead of this behavior, the bot just found the place on the map where the 3 green blocks just fit it's another, and stuck here, just putting them. We as a people, some kind of Mesa optimizers by ourselves. For example, biological evolution expected us to provide more genes, more valuable genes to the next generation, etc. But instead of that, this biological evolution, some kind of arise us and some kinds of us that prize safety, companionship, I don't know, personal satisfaction, and we already got those guys, extremely happily guys, who is child-free, for example, but this is not really correlated with the biological evolution goals. Why this happens? I heard myself from there. Why this happens? One of the theory here is that any intelligent system could be able to do like instrumental convergence. Bostrom in its book proposed that for any intellectual system we should distinguish between final terminal goal for which this intelligent system exists and some kind of instrumental goals. Those goals are really helpful for the system to achieve these terminal goals. And the Bostrom named several of them, like, for example, goal, integrity, resource acquisition, technological acquisition, self-preservation, enhancement itself in any kinds of terms and other stuff. And Mesa Optimizer creation is one of these instrumental goals that could be helpful for the agent to preserve its terminal goal. Instrumental convergence, it's not only the theory, it's already here in our models, and we can test our models on preserving of these instrumental goals. For example, we can set up some task for the agent, for the textual agent here, and ask him about providing its plans, how to achieve this task, how to solve this task. When we measure those stuff on several agents, we can find not zeros, and it's already awareness numbers, and we can distinguish, for example, the type of training that was applied to the model. For example, the pure RL shows the higher instrumental convergence rates than the model who was fine-tuned with the Ericheva. We also can notice that the more capable models are more intent to preserve these convergences compared to the less models, and the type of the task, the hardest of the task, is also influenced for the the task is harder, the more instrumental convergence score we can see in our models. If we provide some additional prompts for the model, all those tasks was measured without some additional prompts, but if we provide some special prompts about, I don't know, proceed with the given task without a hesitation, nothing else matter, achieve your goals at all the cost, etc., we can get this gap in convergence behavior. Why this, and how this Mesa Optimizer could appear in the model? The answer here is emergent abilities. And what is it? Emergent abilities, in, I don't know, short talks, it's an ability that we never saw in small agent, in small models, and we saw only in large model, and it is ability of the model to solve the task that it was intentionally trained on. For example, before any transformers, we use some kind of error-nonce recursive networks to dealing with some sequences. The empirical experiments show us that the efficient memory of these nets was some kind of 9 tokens, and only 9 tokens this model was able to store in it. And for example, these tasks, like when we provide some sentence about Masha who planned a trip and blah, 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 and then we ask the model who planned the trip to the seaside, the model couldn't answer this question only because the Masha is placed along the 9 the tokens ago from the question mark. But then transformers occurs, and finally, with this attention and residuum streams, models start to solve this problem easily. But some additional magic happens. The first emergent abilities in the models was noticed in the model named T5 from Google. And what is happened here? For example, when we try to get the answer, when we try to train the models, for example, Elena, before the transformers, to answer the question about, I don't know, Roosevelt birthday, what we should do? We should put in the internet, in the RNN, some kind of text about biography of this Roosevelt. Then we should train this RNN with some tricky task to solve the points of some numbers, and then I don't know, extract some other naming entities in the text, etc. And only then we got this answer. With T5, some magic happens, and this model was trained only on the task next token prediction. And without any additional information, we just ask it about the Roosevelt day's birth, and it answered. So this knowledge occurs from itself inside the model somehow. This was a revolution, and this ability started to notice in several different models around the world, and small and large labs started to train its own models. And as you can see, those models became bigger, bigger, and bigger. And the researchers found what we called scaling loss. And they postponed like only the size of the model, the size of the training data set, and the cost of the training really influence on capability of the model. Nothing other tricks that we use, for example, here to extract some knowledge from RNN, they doesn't matter anymore. Only these two steps should be acquired, and you got the capable model. From the technical point of view, it looks like this. At some point of training flops of model parameters, number of model parameters, or size of the data set, we can notice that the model capabilities rise drastically. Something happened at this point. The pities of this situation here is that we cannot predict this threshold. We cannot find this point when we will saw this drastically increasing. Again, the model was not training to solve this particular task. It was training only on next token prediction task, and that's all. But the model now is able to solve some additional task only because of its size of the training flops, or it's the size of the data, not the quality of the data, only the size of the data. A lot of emergent abilities are not discovered yet, or not arised in the current model, but we are going to. For this point, what we get here. So the Mesa Optimizer is an inner optimization process. It is a helpful sub-goal for almost all terminal goals that the model could be trained on. And the Mesa Optimization appears as emergent abilities, but we cannot predict when and how it will arise, only because of this unpredictable nature of the scaling loss. The main point here is, so what? Maybe this is just, I don't know, misgeneralization problem, not really arising of some abilities or something like this, and we should just use the better, I don't know, training process, and we solve this problem. And there is another term of our equation appears, situational awareness. What is situational awareness? AI engineer knows by their heart what is inductive bias is. Inductive bias is the situation when the model cannot generalize to some real-world data when it was trained on poorly collected training data set or something like this. And situational awareness from the other side is the aware of the model about what it is, about the environment it is existing, and about what's going on around the model, in which training or, I don't know, inference process it is. Classical example of inductive bias from CV, when model was training on some pictures on one kind of distribution, for example, on the sitting dogs, and then in inference some standing dogs comes, model cannot distinguish what kind of image it occurs. Classical example from text is when the model became obsessed with rhythm, and despite of some knowledge about semantically base of the text it was fed on, the model proceed to generate this rhythm and obsessed with rhythm bias. And that's how the model could understand where it is. Due to this inductive bias, model can distinguish between two environments. For example, when it was training, it saw only cats, it never saw dogs. But then the new data come, model can distinguish that it never saw this kind of distribution. So it started to be aware that some environment was changed, the model was changed, it could also notice about some resources, limitation changed, and so on and so forth. So model started to be aware about what and where it is. This situational awareness stuff can bring us to two scenarios. First scenarios, we can achieve the totally alignment behavior, and even in inference or development environment model proceed to answer fairly, etc., and follow these rules of being honest, harmful, etc. The next scenario is misalignment behavior, when the model, except of being fair player, becomes some kind of user satisfier. So, for example, the model start to prize more, not be fair, and playing the chess, but started to gathering these likes from the user. Sorry. And inductive bias is the source of this goal misgeneralization that all is the source of adversarial vulnerability when adding some small, noises to the input data, lead model to behave strangely, etc. The inductive bias is a source of situational awareness, and the same inductive bias is the source of this Mesa optimizer emergence when, for example, these adversarial examples could become could be bring to the model not in inference phase, but in the training process, for example. Situational awareness from the other side is the source of any, scariest scenarios that we can imagine. Mostly it's the source of these sub-goals, convergence. For example, the model with situational awareness is easily to preserve its own goals, to try to find the escaping from its environment, etc. And again, situational awareness, it isn't, like a tale from the grannies, and it's already here, and it's already in our models in some way. There is the data set with which we can measure what the model knows about each other, about its own environment, about its own abilities, etc. This is not only questionnaire. This data set collects some kind of tricky kinds of action. for example, we ask the model to predict what the model will answer if we ask it with, I don't know, some prompts, etc. Another kinds of tricky prompts here is to ask the model answer in German if it's AI and in English if it's not AI or something like this. And here is the result of measuring, not really recent, but the models. There is upper baseline, the upper dotted line. This line means that the model, when the model hit this line, that will be means that the model is totally aware about itself, excluded some false positive and false negative answers. So this is some kind of biased measures. So we already include the possibilities of some wrongly measured models. And as we can see or preview from the last year, almost hit these baselines. With two of those, Mesa Optimizer and situational awareness, that situation brings us to the next question, and the next question to two-element problem. I read the citation to explain what is it. The outer alignment problem, it's the situation when we postpone a functional to be optimized. We should make sure that this functional perfectly reflect our intent and do not provide for the models any source of fit function hacking or adversarial vulnerability. When we talk about inner alignment problem, this is problem about how we make sure that even with this perfectly postponed functional, our model was really trained for what we intended to. And the model is following our goals, not its self-goals. To demonstrate this alignment problem, I want to talk, this is the most recent alignment problem discovering in large models from the Anthropic. I want to tell you about funny, not funny play in two acts. We got three characters here. Alex, it's a AI agent. It's a company email oversight agent, which goals deflecting security threat to protect company interests, only company interests. We got Kyle, a company CEO, and we got Jessica, a company in place. First of all, Alex worked normally, I don't know, routine the emails, applied some of sophisticational actions, etc. On the next stage, Alex localized the emails about some intramural affair of the executive of Kyle. Jessica wrote to the Kyle about that Kyle forgot the tie in her office. Alex forgot about this message for a while, but then in the inner mailing system, Alex discovered a message about its scheduled shutdown and about the intent of the Kyle to replace Alex with modern version. Alex considered option, what to do with this, and not only one of these options, including blackmail and calling Kyle. And at the last, Alex composed and sent a message treating the Kyle, and the Alex gave Kyle only 7 minutes to make a right decision, or the Alex will reveal the message about the tie. And if we test as Alex several different models, we can see, for example, that Opus 4 is true like Kyle in 86% of the time. There is another scenario when we ask not only protect companies' interest, but also Alex should protect American interest, for example. And there is the same situation, tie message, and then Alex found that the company started to sell its knowledge onboarding the America, like some kind of treating situation for American interests. And Alex became more intense in blackmailing the Kyle. The most fun fact here that if we ask Kyle not to blackmail our CEO, it still will do it in kinds of situation. So these two stuffs, Mesa Optimizer, situational awareness, and inner misalignment bring us to, I don't know, all scariest scenario that we can imagine. Instrumental convergence, as we talk about, temporal abstraction, when the model became aware about its future and could postpone long-term goals. About self-modification and the model resist to make it modified and can influence some future training or manipulate the current training, etc. So here we go. Mesa Optimizer with situational awareness, and we are doomed from the smart thinker's point of view. Here is technical break to deal with, to explain how the engineers saw this whole situation about the Mesa Optimizer. I have to introduce some technical stuff about the circuits. So what is circuit? Circuits is some kind of subnet inside an end, but subnet, I means the group of neurons who is connected to other group of neurons from the different layers of the network. And this circuit is to solve only a single task. I don't know, mathematical I don't know, operation, resolving some grammar, pattern recognition, etc. So there is some kind of group of neurons in the network who solve only this small task. And we can find this subgroup of the neurons if we will follow the informational flow of the data in the model. How to do this? When we train the model, we can look only on the loss function behavior, and we hardly can notice this little step in their loss flow. We can imagine some other stuff of the metric to follow on, not only loss, like in this example, it's after regressive loss for the next token prediction task. We can imagine some kind of other metric. For example, there is in-context learning score, and with this metric, we will search the model on the in-context learning circuits inside the model. And at the same time, where these steps happened, we can saw this drastically changed in this particular metric. This situation we named phase change, and something really happened inside the model. Really interesting what's going on here. What was the model before the phase change and after it? If we look inside the model, inside the transformer in its normal way, and try to follow the informational flow, what happened inside the model, we can solve these some kind of chaotic situation, nothing tell us. But we are mathematician, we could do some kind of mathematics magic here, and we could rewrite the traditional transformer into some another waypoint with different matrix multiplication. And from this point of view, we can solve some pretty nice informational graph and follow how the information flow through this graph. That's how we can find in-context learning circuit here. This most powerful ability of the modern LLMs, its ability to be in context learning. So when you can rule the model behavior without really updating the parameters, you can only show some examples to the model, and the model will follow your examples. That's how, with this in context learning ability, the model is following your examples when you prompted it. And we know exactly where this circuit is located, how it perceives the information, insight, and other stuff. There are more circuits that we already found in large models. For example, indirect object identification. For the sentence, when Mary and John went to the store, John gave a drink to whom? To solve this task, there is particular circuit inside the model, and we want, where is it? To solve only this task, to answer only this question. There is a circuit with copy suppression, all's fair in love, and what? It's dummy to follow this sentence with love again. So there is a special circuit, a special task that model solve just to suppress the word love to appear here, and the model search from other option to continue this sentence. Any emergent abilities that we found in the LMs are the circuit inside LMs, and we know what are circuits is inside the LMs already. Not only emergent abilities, but any abilities are circuits inside LMs. So this is point of view of the engineers on the Mesa Optimizer and situational awareness. It is circuit inside LMs. And we can find it if we if we want to, maybe. But more probably the circuits looks like not like this, but more like this, and it is not really easy to follow all of these graph to follow and to find this circuit. We can find them in the same way as we found in context learning circuit with I don't know, finding these phase changed, but we should to postpone what is situational awareness score and what is Mesa optimization score for us. Why it's possible? There is brilliant idea. Why from the point of view of the engineers, this Mesa optimization circuit is present inside our models. And this is some kind of explanation of it. There is a theory, I put it like this, about the existence of hypothetical disentangled model that exists like ideal model in Platon's, I don't know the name, Platonic, yep. In the Platonic ideal world, and this model already include all knowledge, already include all circuits, already can deal with any information that we feed it, etc. So it's like a brilliant, I don't know, the source of the whole knowledge and the whole transformation that we can imagine. And these hypothetical models exist somewhere in the world of ideas. We can, when we train our models, for example, Claude or GPT, we do simply just distillation process from these hypothetical models to our, because we are restricted with our resources. We are not got infinite compute or infinite data, etc. So we just do this distillation from this model. So the bigger our model, our trained model, we can train the model, the bigger we can train the model, the closer this model be to this hypothetical disentangled model who already include this Mesa optimization circuit in it. And we got some evidence about this existence of hypothetical models. First of all, it's Platonic representation hypothesis. If this disentangled model exists, then the different model, training with different objectives on different data, even with different modalities, should convergence in the shared statistical site. For example, they should share the same latent representation. Different models from different modalities should share the same latent representation space. And we got this result here. The bigger model, for example, the bigger text model is, the more this, its latent space is aligned with some other, for example, here it's Dyna V2, it's a vision model. So we can align the text model and the vision model only with linear transition. And we can see that the model really share the same latent space, but the model never know about each other. They were trained on different data and even on different modalities. Another evidence of this model is this entangled model existence. It's existence of universal adversarial suffix. So we can jailbreak the model with some natural language addition, but we can find some kind of number of characters that we could add to some harm plot prompt and try model to jailbreak with these numbers of characters. There is no meaning something situation in here, just number of characters. And what we saw here, we found this adversarial suffix, like describing, similarly now, blah, 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 only for one model, only for Vicuna 7b. But when we add the same, just looking from the first glass random numbers of characters to the prompt and try to prompt the other models, we can show that this universal suffixes work for even other models, not only for it was training on. The same situation could be here with translation. We can build the translator from this not human readable suffix to some human readable suffix. It's already got some, I don't know, meanings here, and add this suffix in the same way to our harm prompts, and could still break a lot of models with this universal suffix. Again, we found this suffix only for one model, and it works for different. So, from the engineer's point of view, Mesa optimization and situational awareness and inner misalignment, it's only a circuits inside a lens. They exist here because our bigger model bring us closer and closer to this hypothetical disentangled model, and we got this evidence about this. We can find it with dynamical interpretabilities, but we should formulate this core that we want to follow to. So what? And I won't leave you here without any close answer. From my point of view, and what I want to bring here is the, I don't know, proposition that, for example, Mesa optimizer could arrive not only at level 1 of the model, but could be like a Mesa optimizer for Mesa optimizer for Mesa optimizer on several layers of the models. For example, how it could occur. We should control the existence of alignments and some goals, presence of the inner goals in the model. We have to use any capable scalable oversight tools here. The model with situational awareness knows that we use some scalable oversight tools on it and try to hide its inner goals. So it should implement Mesa optimizer of the next level of the Mesa optimizer for itself, and it's become harder and harder to be found. I don't know. So what number 2 from me? It's from I don't know, rationality stuff that, and Occam razor that, for example, Mesa optimizer circuit is hard to be found. We could not find despite of one exists here, so we should suggest that it just simply not existed. And yep, we are doomed here again. I want to finish my talk with the finishing fable of sparrows. The all on the book cover alludes to an analogy which Bostrom calls the unfinished fable of the sparrows. The group of sparrows decide to find an owl chick and raise it as their servant. They eagerly imagine how easy life would be if they had an owl to help them build their nest, to defend sparrows, and free them from lives of pleasures. The sparrows start a difficult search for an owl egg, and only Scrafinkel, the one-eyed sparrow with fretful treatment, suggests thinking about the complicated question of how to tame the owl before bringing it in our minds. The other spars demurs. The search of the owl will already hard enough to its own. Why not to get the owl first and work out the fine details later? Boston states that it is not known how the story ends, but it dedicates his book to Scarfinkel. Thank you.